Okay, in your lab session, you go through the harness test and also the testing for the fatigue test, all this. So today we go back. Previously, we go into chapter 6 for mechanical properties. Today we go back to chapter 4. We look into microscopic behavior. We look at how or why our metal can fail. So today we go into chapter 4. We look into defect. Defect means something already broken, defect, or imperfection that make the metal fail. So we'll cover solidification, then what kind of imperfection that we have. So we go into a few formula to calculate. Okay. So how the solidification of metal works is actually like you are freezing your water in the your fridge. So you start with liquid form. Then liquid form, then you drop the temperature, then they will start to have a solidification. Very, very small solid particles is called nucleus in material science. Okay, so in the liquid form, then you start to have a nucleus. Then after that, it will grow. This nucleus will grow into grain. Into grain. So from nucleus, very small particles, then it go into crystal. So nuclear, then it grow into crystal. So for engineering material, the term that you use in your answer is very important. So if you write nuclear, NuClei, and crystal will be a different meanings in your answer. Okay. So then when it grow until one stage already stable already, you will see all these boundaries. The grain will grow and then it will meet each other, and the edge of your grain will become boundaries. Okay. So this will be under magnification of 5,000, 50,000 times. So in your experiment, I will show you how to calculate the magnification. Right. So previously your lab, I think you go up to 200 magnification. So this one is 50,000. So very, very good microscope. So you see all this is called boundaries, the boundaries. So there are two types of nucleation. So they are homogeneous and heterogeneous. Homogeneous, homo means same. So means the pattern that you see under microscope will be the same. Heterogeneous means it's a different pattern that you see. Okay, so we look into homogeneous. Okay, so homogeneous, normally they happen to pure liquid metals. Pure means if you have an ion, means ion, 100% ion. Because later we will go into alloy. Alloy means you add additional metals inside. Okay, so this table show you the freezing temperature for all the metals that you see on the screen here. Heat of fusion, surface energy, and maximum cooling observed here. Right. So all these are collected experiment by experiment. And for your assessment, remember we are using unit SI. All right. So this is a very important statement. For nucleus to become stable, that it can be grown into a crystal, it must reach a critical size. I mean, the word critical size, it means before we can say that, like for example, for this is start to form a nucleus. Then how we quantify? How do you quantify that this one already stable? We quantify by critical size. So there's a calculation for this critical size. Okay. So when there's a starting, when let's say your critical size is A, say if your size is less than your critical size, it's called embryo, like a small baby inside your right inside a mother womb. So you haven't come into the final shape, right? It's called embryo. So once it have larger than the critical size, they call nucleus. Okay, so this is how you quantify either is embryo or nucleus. So there's a calculation to find the critical size. So the parameter we use for critical size is as what you see on the table. We can quantify using temperature or energy, right? Energy, and also the cooling also linked to temperature. Okay, so when you form a liquid, then from the liquid it temperature start to drop. Then you a small like chicken pox like that. Right? So this is called embryo or nucleus, very small. Then when it start to grow, one layer by one layer, until it reach the critical size, right? So critical size, if you reach under stable already, then you can name it as nucleus. Then it grow, then it become the boundary condition. So when you form an energy, when you form when you form a homogeneous nucleation, so you talk about energy. So when you form, you release energy. So you want to become from solid state to liquid state, you receive energy. Okay, this is like your physics lah, the state of matter, state of matter. From you have a few state lah. So you have liquid, you have solid, then you have gas, right? So you from liquid down to solid, you release energy. You release energy. From solid to liquid, you take in energy so that you're able to vibrate, right? So in chapter 1, chapter 2, even chapter 3, you learn about the atom size and all this. So when talk about energy, means the vibration of the nucleus. Okay, so there are two energy here, bulk energy and surface energy. Okay, so let's say we put a lead, PB, a lead. So let's say we have a PB, a pure metals. So when we cool down to its equilibrium freezing temperature, the energy will transform the liquid to solid with the different energy delta G. This is bulk energy, delta G, V. You see the small sub V here is the volume. It means for volume. Okay, so this is the table that we'll be using. I'll come back to this later. So there's an equation for this nucleation. So if the delta G, right, if we change delta G, for nucleus radius of R, like you see on this figure, so there are lots of patterns of nuclear that we have. This is a perfect size, sphere and cap and so on. So each one of it will give you a different size, then you can calculate for your free energy charges. For example, if you have a spherical, this one, we can use 4 divided by 3 pi r squared. This is a volume calculation, right? Volume of sphere, 4 over 3 pi r cube, multiply by the energy, then you get the energy. So this delta G is per volume. It's per volume. Okay, so this is derived from experiment also. So how do you read this graph? So on the left is your energy, positive, negative. You know, energy, positive means you receive energy. Negative means you release. Positive you receive. Negative means you release energy. Okay, and this is the radius of the particles. Right. In chapter 3, you learn about the radius of particles. You link with when you learn about the cubic, right? The cubic structure. You learn about the A and the R over here, right? So you learn about 3 crystal structure, right? BCC, FCC, and HCP. Okay, so your coming test, you're going to ask you one of these lah. So go and study either these 3 crystal structure, right? So the first curve here is your driving energy. So you're given by 3/4 pi r cube delta Vg. What is the volume equation? 4/3 or 3/4? 4/3. Okay. So there's a typo error on these slides. Okay. So you follow my previous slides. So then another one is the retarding energy. They give you 4 pi r square and the gamma. Anyway, this is just on the graph presentation, right? What is important is this total energy, delta G total, this one. So this, the peak here, will give you the critical radius. Give you the critical radius that can use to quantify either is embryo or nuclear or nucleus. Okay. So this is this delta G here will give you to quantify whether it's still growing or it's still not stable or already stable. Okay, the rest you read on the slides. Okay, so just now we have 2 kind of energy. One is to create surface, which is delta Gs is to create surface 4 pi r square, and then the gamma. Okay, so again, the formula on the slide here is wrong, typo error. So when you do revision, take note on this typo error here. Okay, so basically this is the formula that we might access you, but anyway, if you see this formula come out, normally you'll see this kind of graph, and on the graph you'll see formula on the appendix. Okay, so I want you to see one of the things lah. Okay, so means just now we already cover this critical radius. The main purpose is to quantify whether is the process, the solidification process, is already stable or not stable. Right? So you can find the relationship with the critical size R here with all the parameter that you see on the graph, like free energy and so on. So total free energy equal to 2. One is driving energy, one is retarding energy. One is for surface, one is for volume change. Right? So there are 2 types of energy. I go back to the previous slides here. So to do solidification, you need 2 energy. One is volume free energy and surface energy. Okay. So volume energy basically is to change the state either from liquid to solid. And then one is change state. Okay, the keyword is state here. Another one is the surface energy. You need to form surface layer by layer. Okay, so there are 2 types of energy. There are 2 types of energy. is in solidification. Okay. 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 Then you do some development or derivation for your formula. Okay. You differentiate with the R. You do differentiation of the R. Why we do differentiation of R? You learn about your mathematics, the graph, right? As you can see, the blue line is what kind of graph? Linear, quadratic, or polynomial? Quadratic. Y equal to ax squared plus bx plus c. How you find the maximum point or minimum point of the quadratic? You dy dx, right? Okay. So what value you know that it's already reached the peak on the curve? Is dy dx equal 0, right? So same. This is why we have this differentiation procedure. You dy dx, your x is what? Radius. Right? Your y is your energy. So when you do your differentiation here. So this one, you know lah. So this one doesn't matter because it's a constant. This one also 4 pi gamma also constant. So what you do, you pull all the constant out. Then you do the differentiation. So for example, this one become 3r square. This one become 2r. Okay. Then you equal 0. On the left hand side become equal because you want to find the peak of this curve. Right? So when you do differentiation, you will get this equation. And you rearrange, you'll get R star equal to minus 2 gamma delta GV. So you link, gamma is what? Gamma is a surface. This one is volume or state changing. Okay, solidification involves two process. One is change state from liquid to solid or solid to liquid. Then it go through layer by layer. Layer by layer is the surface. It's the surface. So you link by 2 surface energy divided by the change of volume energy. And it's negative. It's negative. Okay. Which one? This one? Retarding is the, retarding is the surface. Same thing. Retarding means it's a positive side, so it's receive energy. Retarding. Driving means it release energy. Okay. Okay, we are done with the how to find the critical radius. This is very important formula. It's very important formula to calculate the critical size. Okay, now we find the relationship between critical radius versus undercooling. Okay. Now, greater the degree of undercooling delta T below the equivalent melting temperature of the metal, the greater change in volume of your delta V. As you can see here, it's an exponential over here. Okay, so the change in free energy due to surface energy, the S, does not change mass with the temperature. Okay, so means the volume, this one, the volume, this state one, it change with the temperature. But the surface one is not much with the temperature. Okay, now basically this surface one is more on the contact between molecule. If you have an alien atom, You put inside alien atom there in the pool of liquid, they will stick to that alien atom. Okay. So if you see the critical radius formula, is mainly determined by delta GV. So if you change the denominator, you will change the value significantly. Okay. Okay. So we change to another graph. Okay. So this graph is critical radius versus temperature, degree of undercooling. So you see this 500 drop to 0. The nucleus, when you drop temperature, the nucleus is increasing or decreasing. The radius is increasing. Okay, 10 power 7 drop to 10 power 6, -6. Okay, so on the bottom of the blue line is called embryo form. The dot here, the blue line actually consists of small dot. Okay, yeah, this blue line, this is delta T. This is delta T. This is critical radius R star. Meaning all this at this certain temperature, you have one reading of R star. Here also another R star. Here also another R star. Okay, so different temperature will give you different value of R star. So from here, below the blue line is called embryo. Above means stable. This one already stable. Above this one is stable, then you will form boundary condition or boundaries. So this one you read, huh? Okay. So there's a formula to calculate based on heat fusion. So there are two formula for critical radius. 2 gamma Tm delta H F delta T. Okay. Okay. So for example 1, we see how we apply this formula. Okay. So you're given it asks you to calculate the critical radius in centimeter. Okay. So normally we in engineering material we'll use micron or mm, 10 power something mm, right? Of homogeneous nucleus that form when pure liquid copper solidified. Okay. Assume delta T undercooling is 0.2 Tm. Tm is a melting temperature. Use data from the table below. Okay. So from the table below, you are looking at pure copper. Which one is copper? This one, huh? So you're using freezing temperature, this one. Heat fusion, this one. Surface energy, this one. Maximum undercooling is this one. Okay. So calculate the number of atoms in the critical size nucleus in this undercooling. Okay. Undercooling is where they you form solids. You can see some nucleus. Yes. Okay. So you means you start to see nucleus already. Okay. Here lah, the one that I draw on the whiteboard here lah.
So it's like at the phase where it starts to turn into a solid.
Become stable. Means you reach the radius critical. This D lah, but you reach the radius critical already. Means this temperature will give you this stable. You can start to see under microscope this size already. Okay. Okay, so by using this table, you do calculation. All right. So what is the critical radius? Calculate. No calculator, you have handphone. Okay, so this one, okay. So first you convert delta T equal to 0.2 melting temperature. Okay, CU. So melting temperature is 1083 Celsius. You change into Kelvin, then multiply by 2, or you can straight away read from here. Okay, because some table didn't give you the Kelvin, so remember to change into Kelvin. So delta T equal to 271 Kelvin. Okay. Then gamma is not given. Gamma is given here. So gamma is a surface energy. Okay, this one. The gamma is a surface energy. 177 10 power negative 7 joule over cm square. And this one, heat fusion. Heat fusion, 1826 joule over cm. Melting temperature, already calculate just now. Melting temperature. Okay, so on the table, you see freezing temperature. It actually also means melting temperature. So you have all the value already. What is the answer for critical radius? What's the answer? 7.15 minus 11. What? cm. Correct. You agree with this answer? This one. This one. You agree? What do you get? Huh? Well, what do you get? Some get 5 point something. cm.
That Celsius down there printed in Kelvin also, right?
Yes.
The under cooling. Okay. Times divided by delta H.
This one so difficult, meh? Huh? 177 10 power -7. 1356.
It would be 9.7 centimeter. 9.7. You mentioned 9.7 is
9.7 minus
8.
8 cm. Okay? Huh? Same. Okay.
Oh,
It's 9.7, 10 power negative 8 cm. Okay. So this is a very direct question. Important is to memorize the equation. So again, there are two equations only for critical radius. 2 gamma divided by delta G V, or 2 gamma Tm divided by delta HF delta T. Okay, and this is a very popular table for your assessment. How do you calculate number of atoms in critical size at this undercooling? Or what do you think? How you calculate? How you calculate if you're given this formula? How do you calculate? How to find number atom?
divide undercooling. Thinking, I'm thinking.
Processing.
Yes. Divide undercooling. No.
What is I asked you to remember 3 member of BCC, FCC, SPC, HCP, right?
Oh.
So copper under what? Go and remember 3 member from here. Popular one. Remember 3. 3 lah. In the table more than 3 lah. So you remember 3 lah. Okay. So copper is FCC. Okay. So previous chapter we learned about relationship between A and R. So here copper A is 0.36, R radius star here is copper is 0.128. So previously for FCC in the table, your R equal to square root 2A divided by 4. Okay. So this FCC, if you forget, go back to chapter 2. Hold on. I did give you the scope for test 1. So yeah, okay. So this is one of the question are going to come out. Okay. So we already established how to calculate the cubic A, how to calculate become here to here is square root 2A. Here to here is 4R, so you equal these two together. 4R equal to square root 2A. Then your R equal to square root 2A divided by 4. Okay. If you forget, go home and revise chapter 2. Okay. So now you're given the A. Substitute this value inside here. Right. So you have 4 atoms in FCC. Okay. How many atoms you can fit inside FCC? 4, right? 4, right? So 1, 2, 3, 4. You get 2 atoms. Plus the 8 corners, you get another atoms. So you get 4 atoms. Okay. Right. Correct, right? For the face one, you got 3 atoms. Got 6 faces. This one got 3 atoms. And then combined with the 8 corners, you get another atoms, 4 atoms. So you have the R there. Just now you find the R star. So it means that when you reach a stable, means your sphere already reached the critical R. When you draw the cubic diagram, this is your D or R. You reach the stable states. So your critical volume size is 3.82 cm cube for 1 cube size. Then it asks you number of atoms. So for copper, your A, how to find volume is A cube. A is given in the table, 3.6 10 power negative 8 cm cube. You get 471 10 power 2. Okay. So volume per atoms, you take 4.7 divided by 4 because you got 4 atoms. You get 1.1 or near to 1.2 10 power negative 2 cm cube. Okay. So you have 3 value there. You already calculated the volume for the critical size of a nucleus. Then for FCC, the unit cell is 4.7. And volume for 1 atom is 1.17. So the number of atom per nucleus, how to calculate? You have three value here. How to calculate number of atoms? You find the volume of the stable radius, or stable molecule. This one, you have the V for this one. V for 1 copper nucleus is 3.8 10 power negative 21 cm cube. Is R star. Then inside FCC, one cube like that is 4.7 negative 23. Then volume per atoms. Your atoms, 1 copper atoms is 1.75 10 minus 23 cm cube. So number of atom in the critical nucleus. How many atoms? It asks you number of atom in critical size nucleus. You understand? You focus on which one? This one. He asks you, inside here got how many copper? Okay. You take volume of nucleus divided by volume of an atom. You take this one divided by this one. Make sense, huh? So you have 325 atoms of copper for one stable nucleus, or one stable atom that already reached stable stage. Inside here you got 332 atoms. Okay? Make sense, huh? Okay. Okay, so next we go into formation of a stable nucleus in liquid metals. So we already completed how to calculate critical size, how to find based on either BCC, FCC, or HCP, you're able to find in one nucleus stable with the R star. You can calculate inside here got how many molecules or how many atoms inside. Okay. Meaning under a microscope, you see a stable, then you can estimate how many atoms inside. Okay. This question can extend to periodic table. Yes, you have atom number. You can estimate how many weight of this one. One dot inside the liquid that already stable. How many gram of this one? You can, right? You know how to do, right? So in periodic table, let's say copper is here. So under copper, I give you one number below. So this is what? Gram per what? How many molecule? Mole. One mole got how many molecule? Number of Avogadro. 6.023 10 power 23. So here in the periodic table got one number there. That number equal to this atom. So from here you can calculate one atom how many gram. You take this one divided by this one. This one divided by this one. Makes sense. You get one number. So let's say this example, you get 322. Take this number, multiply that one. Oh, here you already get one atom, how many gram already? You take this answer, multiply that one. So one solidify at this one nucleus equal to how many gram? Enough? Okay. Just now is homogeneous. Now heterogeneous. Heterogeneous means you have impurity already. Impurity means you got alien atoms inside there. So when you have this impurity, is going to lower the critical energy required to form a stable nucleus. Okay, so I'm going to explain about this one. So let's say this is a nucleus and this is the solid that form. Theta is the contact angle. Okay, so for heterogeneous nucleation, the solid nucleating agent or the impurity must be weathered by the liquid metals. Also, the liquid should solidify easily on the nucleating agent. Okay, so this is Okay, so this is liquid lah. So this is liquid. Let's say this is copper. Then let's say you have an alien atom there. Let's say you have a nickel Ni inside there. Or carbon lah. Let's say carbon lah. Carbon. On there. Okay. Then you put under microscope. So this dark color is a carbon. Carbon surface. Okay. So you will form an angle of contact surface, solid and liquid. Okay. So this one, it will create a low contact angle between the solid metals and the nucleating agent. Okay. So means this is the, let's say this is a carbon. This is the liquid copper, for example. So when liquid copper and carbon, they join together, they will form a solid. It means they solidify already. So there must be a surface for it to grow. So the copper will grow on the carbon. So this one is what they grow lah. So this is on theoretical. So we choose a sphere shape to form. So this is a solid that this solid is a copper solid. This solid is a copper solid, not the carbon, not the carbon. So they form an angle. Okay. So for heterogeneous, it take form because of alien atom or nucleating agent. So the surface energy form the stable, lowering the materials. So for homogeneous is delta G. For heterogeneous is the gamma, the surface. So for solidification, again, there are two mechanisms. One is change state from solid to liquid or liquid to solid. Another one is the contact surface that give you the surface energy. They go by layer by layer. So there are two types. So just now, the example just now is homogeneous. Now we're looking at heterogeneous. We have an alien atom inside there. Okay. So this one you read lah. Read. Okay. So this one is because of the alien atom, it pull down the total energy needed. So the undercooling temperature also lowered. Okay. Now this is already formed a crystal just now from nuclear. Then it start to grow into crystal size. So crystal size is your chapter 2 things. Okay, then it start to grow bigger and bigger. Then it will join together, squeeze each other. Then they will form a grain boundaries. Okay, crystal, they grow bigger enough, they will call as grain. So grain with grain between grain, they give you grain boundaries. Okay. Okay, the rest you read. If you see the word polycrystalline, means poly means many. So polycrystalline means many crystal. So crystal in metals, they are called grain. Surface between grain is called grain boundaries. Yes. Or if you are good in cooking, you like baking lah. You know roti when you put in the dal, not dal lah, but on the plate then you put inside oven, it will grow, right? It will grow. So when it grow, it become like muscles like that, like 4 pieces of muscle joined together. So the joining part is the grain boundaries lah. Like it grows like that. So when the two matured dough join together, you see boundary. So boundary you can peel them off one. Okay. Yeah. So you like a grain boundaries lah. Okay. So it depends on how you imagine. So if relatively few nucleation sites during solidification, then you will form coarse grain structure. Means very big, very big. If you have a few nucleation sites, but you have many nucleation sites, means you have a lot of chicken pox. Then you form a fine grain structure. Yeah, so you just imagine you have two sides, one chicken pox like 4 dot like that. This 4 dot will grow. Then they form a very big coarse grain structure. If you have a lot of chicken pox dot, then they have no space to grow, but they form very small dot lah, very small grain. They call it fine grain. So like how you think as a mechanical engineers lah. Okay, it's more on the space that you have and how it forms. Okay. So in engineering, we use casting with fine grain structures because it's most desirable type for strain and uniformity. Okay, so means that if you have fine grain, later we look at the defect and all this. Fine grain means you have it's more harder for it to move around, right? Okay, there are two type of grain in casting, for example. You have equal axis grain and column grain. Equal axis grain, they grow about equally in all direction. Column grain, they solidify rather slowly in the presence of steep temperature. So what does it mean? I give you this diagram, you understand already. If you do casting, you pour the hot molten liquid. Where is the cool surface? Here. The mold is very cold. You pour in. Where does it cool down first? The wall, right? So this one it cool down equally, then you form a very small grain here. But then because of this already formed still here already still very hot. So the energy the energy of the hot temperature you must pass through this one, right? It must pass through from the center to the wall. But this one blocked already. So it will form a very long grain there. Then here already form. So this will be the first layer form. Then it will slowly cool down from here to here. It will take some times from here to here. It will form a very long grain. This one normally when you do casting, the metal you break, you see the wall will be this one, and then the inner will have a long grain. Okay, it's called column grain and equal axial grain. There are two types because of the temperature. Okay, the column grain because of the steep temperature gradient between in and out. Okay, so how we ask you question about this kind of theory? We normally you explain using schematic drawing. This you draw a mold, you draw this small grain here, then you draw arrow, you write equal axial grain. Then you label this one as mold, then you label this middle one as a columnar grain. Okay. Okay. So how the equal axial grain form? They create high concentration of nuclear during solidification, a condition necessary to produce this equal axial grain. Okay. So this one is because of the uniform. This is very hot temperature. It is cold temperature. So if you pour in, So this section, if you look in big one, so this is a wall. So they will, this is liquid. So they will form chicken pox along the, like chicken pox lah. So they will form chicken pox, then they will grow. They will grow like that. Okay, because this is the temperature is quite equal. It quite balanced when near the wall. But after a certain distance from the wall, the temperature difference is there, like 1 or 2 degrees Celsius, something like that. Then it will take some time to travel from center to this one. So there is a gradient of temperature, delta T here. Then center one will form a columnar grain. Some process they need to warm the mold, some not required. It depends. All right. So again, the keyword to explain these two type of grain is the gradient. The gradient of your temperature. Thermal gradient. Large thermal gradient apply for columnar. And this one is because of the high concentration of nuclear at the wall there. So this is the slab casting. This one is too young.
The commissioning and the steep run-up curve show that the cooperation between us and SMS was highly successful. On the 5th day of production, 50 heats were already cast in one sequence. Since then, production has been running splendidly.
This one you view when you have time. Okay, so this one is more on like what is the grain structure for industrial casting and all this. So ingot is the one that come out from the hot mold. The hot mold. Then this ingot is the one that we learned in your processing, like hammering, all this lah. Not in our lab lah, not in our lab. So this is another schematic table for casting process, right? So casting process, you pour in the metal from the top, then you have a mold, then you have a cooling at this both end. Okay, but this one I won't ask you lah. Just watch the video how the. Okay. This one is a single crystal casting. You see how they form. Okay, so this one is another one, continuous casting. It's also is a process lah. So I won't ask you how to do that. Okay. Okay. So this one, we stop here. Later we go into concentration. Stop here. We have maybe 5 minutes breaks. We continue 11:15, right? 11:15.